Well, hello. My name is Matthew Wilson. I'm going to be presenting my research paper entitled Understanding Impacts of Severe Wildfire to Arizona Mountain Forest. It's an analysis of two large wildfires in the Madrean Sky Islands. The objectives of the analysis. So I researched two large and destructive wildfires that occurred within two southeastern Arizona mountain ranges. The Bighorn Fire, which occurred in the Santa Catalina Mountains in 2020, and the Fry Fire, which occurred in the Pinaleno Mountains in 2017. Both of these wildfires are described by varying degrees of burn severity. Each consumed large portions of high elevation coniferous forest, and each fire also followed a previous large and destructive stand replacing wildfire event. Within the analysis, I aim to first provide a remote sensing index-driven fire effects analysis to identify burn severity and intensity of each fire. Secondly, I used a change detection analysis to force structure loss. And third, I did a vegetation recovery analysis following a 5-year period to show any divergence from pre-fire conditions. Most specifically, I hope to provide an accurate estimation to the areas that are likely to have undergone forest type conversion. The study area. So here's a visual representation of the location of the mountain ranges in southeastern Arizona. Santa Catalina Mountains are located in northeast Pima County, and the Pinaleno Mountains are located in southwest Graham County. A bit of background. So historically, wildfires within the Madrean Sky Islands were rarely large and mountain wide. Often fires burned at low intensity, particularly within high elevation, pine dominated or mixed conifer forest. The dendrochronology record suggests that the maximum interval between pre-20th century wildfires typically ranged from about 10 to 30 years in pine dominant forest and range between 40 to 50 years within mixed conifer. Fire itself is an important ecosystem control mechanism that enhances forest condition by reducing deadfall, underdeveloped vegetation, and understory fuel loading that would otherwise contribute to a higher burn intensity and severity. Increases in the human interactivity with the landscape following the 20th century settlement of southern Arizona increased wildfire suppression within lower elevations, leading to a century of fire exclusion. This is exemplified by the 1930s U.S. Forest Service, quote, 10 a.m. policy, which stated that a fire should be put out by 10 a.m. the following morning following its initial discovery. Significant grassland reduction from livestock production and grazing, wagon roads, logging, etc., meant that surface fires could no longer ignite or spread wide distances throughout the higher elevation terrain. Since the year 2000, the two mountain ranges in the analysis each experienced two significant stand replacing wildfire events spanning almost the entirety of each mountain range. In this figure, you can see each of the study fires, which are identified in red, in comparison to the fires that had occurred in previous. The Aspen Fire occurred in 2003 in the Santa Catalina Range, and the Nuttall Complex Fire occurred in the Pinaleno Range in 2004. Notice the study fires had quite a bit of overlap from each precedent wildfire. Response to high severity fire. So high severity fire and stand replacing wildfire typically have the greatest impacts to forests with historic frequent fire regimes. The long-term effects of high intensity and stand replacing wildfire remain unknown, especially to the unique ecosystems of the Madrean Sky Islands. Conifers in particular have limitations to seed dispersal and regeneration. Their seeds are large and are not widely distributed from wind, with seeding years also varied by drought stress and other environmental factors. Often, seedling development are constrained to surviving reproducing clusters of conifer trees. Um, Less surviving clusters from stand replacing fire will reduce available seed supply. In many cases, conifer regeneration are often outcompeted and overtopped by species that can resprout from rootstock. Examples include oak and New Mexico locust. And since they're unable to access, or rather, since these species particularly are able to access resources much faster and are more drought tolerant. Further, reduced precipitation associated with climate change is expected to add additional pressures to pine-dominated forest and may also drive forest type conversion. Pine recruitment declines independently with decreasing moisture availability. So using a change detection with remote sensing indices is becoming a much more common practice with land managers and help provide forest managers with accurate information regarding effects from forest disturbance. So the photo I've included, it was taken on Mount Graham, located in the Pinaleno mountain ranges. You could see the examples of primary succession and early secondary succession. Uh, Primary would include the massive amount of grass that's regrowing in place of where conifers used to stand. And secondary succession would describe the yellowing aspen. Forest recovery is likely to occur in areas with aspen regeneration, while areas with grass are unlikely to recover to pre-fire condition. Fire intensity. Fire intensity is the product of the amount of fuel consumed per unit area and is closely associated with the consumption of fuel. Essentially, the more dry fuel, the higher the likelihood of increased fire intensity. While high fire intensity is often results in high severity fire, fire intensity is independent of fire severity. These graphics present the results of fire intensity of each fire using the difference burn area index for Sentinel-2 imagery. Specifically, this index was chosen to take advantage of the red-edge sensors unique to the Sentinel-2 multispectral instrument. From the representative figures, I made general assumptions regarding the impacts of each fire and concluded that the Fry Fire consumed a much larger amount of fuel, while the Bighorn Fire likely consumed less fuels. Each basically coincide with the moisture availability between each mountain. The analysis of precipitation patterns showed the Pinaleno Mountains likely sustained significant vegetative growth prior to the Fry Fire, and slight trends in monsoonal rain and snowfall patterns 24 months prior to the fire likely contributed to significant fuel loading in the understory. In contrast, the precipitation patterns in the Santa Catalinas revealed a general downtrending of available moisture that likely reduced vegetative growth. In areas of high fire intensity within the Bighorn fire scar, fuel loading may have increased, resulting from drought-related mortality or from dead and down material that resulted from the precedent aspen fire. Fire severity. So fire severity identifies the measurable impacts of fire to soil, plant stems, and canopy structure, which is mostly correlated with heat energy released from fire. Raster images on burn severity were calculated using a normalized burn ratio plus. This index is statistically proven to be more accurate when estimating burn severity when compared to traditional MBR calculations. The difference, MBR plus, was calculated to compare pre-fire and post-fire imagery to indicate areas that had experienced varying levels of burn severity. I reclassified each of the pixel reflectance values to provide better insight on the fire effects from each fire. And interestingly, about 3% of the total area of each fire burned at moderate to high severity, and roughly 35% burned at low to moderate severity, suggesting that there are relatively similar effects across each mountain range. However, the Bighorn fire burned a larger total area when compared to the Fry fire. Vegetation density. So the forests within the Sky Islands contain conifer species that are adapted to high fire return intervals. Particularly, these conifers select phenotypic traits that enhance survival rather than reproduction, and this leads to a slower growth rate. Disruptions to forest disturbance from fire can result in larger impacts to forest health conditions. This includes abnormally dense forests that tend to have higher mortality from wood-boring insects, fungal infection, and drought. The increases in forest density often imply alterations to historic fire regimes, leading to an abundance of fuel buildup. As a result, increases to fire severity within each mountain conifer forest are likely to impose long-term impacts to preferential microclimates and soil conditions that would be optimal for regeneration. As stand replacing wildfire becomes increasingly common in the Madranski Islands, subsequent wildfire activity is likely to occur within similar footprints. Heavy fuel loading associated with tree mortality from an initial fire show increases in moderate to high severity burn in subsequent wildfires, which impact future vegetative structure. This photo was taken on Mount Lemmon, which is in the Santa Catalinas in mixed conifer. It identifies relatively good density management, which helped to preserve the stand through the aspen fire. Just take note of the blackening of the stems, which are representative of the flame lengths at the time of the fire. Vegetation density comparison. So I reclassified NDVI values calculated from pre-fire imagery and imagery 5 years post-fire to summarize the vegetative condition and density on each mountain. At 5 years, it was expected that fire-related mortality had subsided and the vegetative recovery process had started. Here is the density comparison for the Bighorn fire. Should be noted that about 44,189 acres of vegetation experienced changes in the Santa Catalina Mountains and was most noticeable at higher elevations. Here's the vegetation density comparison for the Fry fire. Notice some clear changes also at high elevations. Forest type conversion. So for this analysis, I used the MBR plus indice to compare pre-fire and post-fire condition. So this was measured at a 5 year post-fire condition. So the pixels with reflectance values that were less than negative 0.1 were labeled as enhanced regeneration. And any pixels with values that met or were above the threshold for low severity fire. In this case, I chose a reflectance value of 0.1. After 5 years, were labeled as not likely to return to pre-fire conditions. Therefore, 5 year regeneration patterns are presented within each of these maps. And 5 year regeneration patterns are also often indicative of observable patterns even after 14 years, suggesting that the results would be representative of forested area that have been reshaped and likely representative of forest converted by each fire. So the Fry fire was far more destructive and had a much greater impact on forest structure per area than the Bighorn fire. It is likely because the Bighorn fire burned in much of the same footprint of the Aspen fire, and the previously burned areas were likely already type converted. Similarly, wow, can't say that word. Sorry. Across both fires, areas that were unburned by previous fire exhibited more continuity of potential fire, or excuse me, potential forest type conversion, which suggested that areas with fire perimeter overlap are not necessarily more disposed to forest type conversion by the second wildfire. In fact, reburn potential is limited by fuel and vegetation consumption by an initial fire and is driven by the amount of time between burns and site productivity. This suggests that sites that initially burned at moderate to high severity tend to reburn at predominantly low severity. And yeah, thank you for taking the time to view my presentation. Thanks to my professors and peers, the University of Arizona GIST Master's Degree Program. And also, I just want to acknowledge my employer, the Arizona Department of Forestry and Fire Management, who encouraged me to further my education and help to fund my tuition for the program.